This section will study another example of motion in two dimensions. In this case, what we're looking at is a block that slides on a ramp. It can either slide up or down the ramp, and when it does so, I think it's pretty clear that it's moving both horizontally and vertically. However, what we'll see when we solve this problem is that by appropriate choice of coordinate system, we can actually reduce this to a one-dimensional problem. But let's look at this motion first. The first thing to notice is that the block's acceleration depends on the angle of the ramp, and this angle we usually denote by theta. The direction of that acceleration is going to be back down the ramp. Unlike gravity, which was always downwards, this acceleration depends on the angle and points in the direction back down the ramp. If there is no friction acting on the block as it slides up and down the ramp, then we know the size of the block's acceleration. The block's acceleration has a magnitude of g, which if you remember is 9.8 times sine of the angle. We'll use that in just a second as we solve this problem. We will learn where this value of g sine theta comes from in a future chapter. So let's look at this example. In this case, we have a block that's sliding up the ramp, and when we first look, it's moving at 3.5 meters per second, and we know that the ramp is angled at 20 degrees. So before we get started, we need to do the same things as we always do. In this case, we don't have to draw a picture because it was given to us, but I'm going to go ahead and indicate the angle of the ramp on the picture just so I remember. Now let's go ahead and choose our coordinate system. This is a rare situation where I won't have my y point up and I won't have my x point horizontally. What I'll choose is my x coordinate to point up the ramp and my y coordinate to point perpendicular to the ramp. The reason for this choice will become clear in just a second when we examine the kinematic variables. Well, let's go ahead and look at the kinematic variables. Again, we'll need to look at the kinematic variables in the x direction and in the y direction. And so I'll have to examine my a, my v naught, and my x naught in the x direction, and my a, v naught, and y naught in the y direction. Now, to find the acceleration, we have to just apply the formula that we just saw, that the acceleration has a magnitude of g times sine 20. In this case, that becomes 3.35 meters per second squared, and it's negative because that acceleration is back down the ramp, and we chose our x to point up the ramp. The initial velocity is also along the ramp, and in this case, it's positive 3.5 meters per second because it's going up the ramp. Our initial position is 0 because we chose our origin to be where the block is originally located. In the y direction, the acceleration is 0 meters per second squared. This is because the block is not accelerating away or into the ramp. It's not smashing the ramp apart and it's not jumping off the ramp, and so there is no acceleration in the y direction. The velocity was also up the ramp, and so in this case, the initial velocity in the y direction is 0 as well. And the initial position in the y direction is 0 as well because we chose our origin to be where it originally started. Since all these kinematic variables are 0, what that means is there is no y motion. And that's why we chose our coordinate system the way we did. Ultimately what this means is there is only motion in the x direction and no motion in the y direction, and that will simplify our problem solving. So now let's start to look at part A. In part A, we want to know where the block is located after 0.5 seconds. And this is the question, what is x when t equals 0.5 seconds? So in this case, we use our first kinematic equation. And after we plug in our values, we see that x equals 1.3 meters. And what this means is that the block was located 1.3 meters farther along the ramp. Now, if we wanted to, we could find its position relative to the table, both horizontally or vertically, but this is sufficient for now. In part B, the question is asking, when does the block reach its maximum height? And this is very similar to those projectile motion as well as those free fall problems we've been studying. In this case, what we're asking is, what is t when v sub x is equal to 0? So we write down our second kinematic equation, plug in our values, and what we find is that t is equal to 1.04 seconds. And so it takes 1.04 seconds for it to reach its maximum height. In part C, we're asked to find what this maximum height is. That is the question, what is x when t equals 1.04 seconds? So we write down our first kinematic equation, fill in the values, and what we find is that the maximum height is 1.83 meters further along the ramp. Now, if the problem was really asking for how high it was above the table, we could find that as well by using our triangle. In this case, because the angle is 20 degrees and the hypotenuse is 1.83, then the vertical distance is 0.63 meters, and so this is 0.63 meters above the table. In part D, we want to know when the block returns to its original position. This is the question, what is t when x equals 0? And so we go ahead and use our first kinematic equation, plug in values. And what we see here is that we get a quadratic. And this quadratic will have two solutions. The first solution is when t equals 0, which makes sense. It was at its original position to begin with. But the second solution is the one that we're more interested in. So we can go ahead and write that down, solve it, and we find that t is equal to 2.09 seconds. And so ultimately the block returns after 2.09 seconds. Now, like we saw in the projectile motion problem, as you can see, this is double the time to maximum height. The only slight difference here is due to rounding errors, but because there is no friction, the time it takes to go up the ramp is the same as the time it takes to come back down. And so now we can find what its speed is when it reaches the original position, and given what we've seen in the previous section on projectile motion, I think you can guess that it's going to be the same as when it was first launched. But let's go ahead and check anyway. What we're being asked for is what is the magnitude of v when t equals 2.09 seconds. But because there is no y velocity, this is really just asking for the absolute value of v sub x. So let's go ahead and solve for that. We go ahead and plug in our values, and we solve, and you can see that v sub x is negative 3.5 meters per second, which is the negative of the original value with which it was originally sliding. And so its speed when it returns to its initial position is 3.5 meters per second.